So, welcome to the third lecture on module 11, which is on memory testing. So, till now we have been discussing about testing ATPG for various type of sequential circuit, combination circuits offline, and then we have seen that if you are going for offline testing, that is using an ATE, so there can be problems in situ testing. So, we have gone to a built-in self-test mechanism of test and so forth. So, the wide range of coverage we have done till now comprises mainly of sequential and combinational circuits. So, sequential and combinational circuits, if you think, they are actually composed of gates, flip-flops, wires and all those things. But there is another very important module of VLSI circuits, that is actually the memory. So, excuse me. So, in case of memory testing, as you have to observe that it will be quite different from the other digital testing of synchronous, asynchronous or combinational circuits. There is sequential and combinational circuits. Why? Because the idea is that all the digital circuits, sequential, combinational, whatever we discussed till now, were comprised of logic gates and flip-flops. Flip-flops are themselves comprised of logic gates and all. Okay, but the memory blocks actually work in a very different way. See, the idea is that what is the memory block like? So, you have a block of RAM, DRAM, SRAM, whatever. So, you have lots of memory cells over here, and they comprise the value of 0 and 1. You can write it and you can read it back. So, it is unlike, it is unlike the operation. It is unlike, where the idea is that you have to compress a large number of memory cells in a very small area. So, this is unlike your D flip flop where you can store your area. So, if you have to make a memory element or a memory block of say 1 GB using only flip flop, it will be so large that you cannot make it, fabricate it or sell profitably in the market. So, if you have to make a 1 GB of RAM kind of a stuff, so the technology to be used is very different, because you have to have a very compressed area. And one more thing, the memory is very symmetric, because it has memory cells, you can access the cells, and whatever you can do is that you can read the cells, you can write the cells, that is the only thing you want to do. There is no other logical operation involved in the memory. But if you comprise of the flip flop, so that also stores a bit 0 or a 1, but actually it is also involved in lot of what you can call logic operations. So, the philosophy of using a flip flop and the philosophy of using a memory is a bit different, even if their job is the same. So, in the case of flip flops, they are not basically symmetric. So, in sense of a memory. So, in memory our idea is that we have a symmetric structure and we have to compress as many bits as possible, and the operation is only read and write. So, we have to compress it, and in case of flip flop the philosophy is a bit different. Here also you have to store a bit and retain a bit, but it is also involved in lot of what you call combinational logic formation, logical operations. So, we cannot have a symmetry. So, that is a bit different, and so in case of flip flop based memory or in case of flip flop itself, so you can have spare to have somewhat a larger area because it is non-symmetric and the purpose is a bit different. But in case of memory, as it is only read and write operations, it is very symmetric in nature. So, you have to compress as many bits as possible using a very small area. So, that is somewhat philosophically they are different. So, that is why it is necessary, it is different fault model and test techniques for memory block, because of the very basic design philosophy, and also the memory block design. So, you might have heard about some 10 years ago. So, when we had 1 GB of hard disk, it used to be a very good thing, okay, and RAMs were 512 MB or 128 MB kind of a thing. But nowadays our hard disks are in terabyte size, and your RAM and your ROM CD, your what you call the DRAM and SRAM what you are putting in your PC, they have gone to 4 GB or 8 GB. So, that is why the memory technology is increasing very fast. But in spite of that, in spite of your memory size increase, the size of the memory chips or the area of your computer does not increase. So, what we are doing is that we are using very advanced technology. So, in the same die area or a very minimum increase in die area, we are trying to put as more bits as possible, that is being compressed. That is why it is saying that memory technology the capacity quadruples every 3 years, which leads to decrease in memory price per bit that is being stored. That is what I was saying, that you cannot, your size of the RAM or size of RAM chips have decreased a lot if you compare 10 years back, and still your amount of memory that you can pack in or your capacity has increased. So, that is what the same area we are trying to put as many bits as possible in a very compressed layout fashion of the memory, so that the cost per bit is decreasing. That is why our money is of price of the RAM chips are decreasing and the capacity is increasing. All that is happening because of the extensive increase in fabrication technology. So, that is what he is saying, high storage capacity is obtained by increase in density, which implies increase in size of the capacitor which is used to store a bit. So, the basic idea is that there is some charge storage device which actually stores the memory. So, we are not going to a memory, it is not a memory design class. So, you can look at any analog design or memory design book. So, there are different memory structures like EEPROM, PROM and RAM, DRAM, SRAM, lot of different architectures are there. But the basic idea is that there is some kind of a capacitive element or some other element you can take quote unquote, you can say, for the very modern day memory. We have some some kind of a capacitive type of charge storing device, where you store the charge if the value is to be stored 1, and otherwise you store a charge of 0, I mean if the value to be stored is a logic 0. So now what is happening? So nowadays very new technology, I mean new materials or fabrication technologies are dielectric materials like barium and all those things, all these are new, I mean what do you call fabrication technology using different dielectric materials are coming up to build the capacitors, I mean to charge storing devices, which will have to have a greater capacitance and maintain the same space. That is what is the idea, is that you, with this lot of new technologies like this type of dielectric materials, and these are actually physical layout stuff which you can find out from any standard physical design book or physical design lectures or physical design stuff in the web, but we are not going to cover in this lecture on this testing, or because this coverage mainly on the memory design. But the very basic issue I want to emphasize is that by using lot of advanced fabrication technologies, using newer and newer types of the dielectric materials used for doping and making your ICs, you are able to compress much more stuff or much more memory capacity into a small area. That is by increasing the capacitance, by keeping the same amount of capacitance you can assume, and in a very less amount of area. That is greater capacitance to be maintained in this same physical space. That is, in the idea is that, in other words, you are having more capacity, you are increasing in the less amount of space. Further, memories are now techniques are also being developed so that you can access the memory very fast, okay, with the fast page mode access is there, extended data output, synchronous, and all the double data rate. So all these new technologies are coming up in memory design. Like fast page mode means you can very quickly access the memory, and pagings are faster and all those things. I mean details you can find out from any memory design book. And also, I mean what you call double data rate, SD RAMs, and all those things are advanced in technologies. That is, double data rate means in both the clock edges you can access data or write data from the memory. So the idea is that the memory technology is advancing far and by leaps and bounds, like as we are going for also for the increase in your combinational and sequential circuit design also is slowly shrinking in nature by using deep submicron technology. Similarly, in the memory paradigm also, we are having higher memory sizes in same area, faster memory access rate, higher reliability, double data rate, etc. So these are all the features which are increasing also in the memory area. So what happens is that there are a lot of failures, as in the cases of simple sequential circuit or combinational circuits, memory chips are also prone to failures. Okay, so but there are 2 or 3 philosophical differences which will make memory testing bit different from what we have been doing from the sequential and the combinational circuit testing. In sequential and combinational circuit testing, what we have seen is that if the circuit is having any defect that is found out in the testing, you throw it off and you ship only the good chips which are detected to be fault free. But here if you try to do this with the memory, then you will going to find that around only 1 or 2% of the chips, or even lower than that, will be the yield. That is, if you are going to test your memory chips and find out that I will throw out all the chips as defects, then you will land to a situation that your defect, your yield will be 1% or even less than that. Now what is the idea? In case of memory, as it is very symmetric, so we are using such a technology so that we are trying to pack as many stuff in a very small area, die area as possible. So if you make your fabrication in a very stuffed manner, on a very stacked way manner, so lot of probability of faults increase. So what is the solution? So unlike general circuits, we do not discard any faulty memory chips. Now why is that? If you start doing it, so in the end you are going to have what? You will find out that only 1 or 2% of the chips you can sell in the market. So you cannot tolerate this. So one thing is that you can actually make the memory layout in a bit sparse manner, so that probability of faults are there less. But then what will happen is that you have to the chip area will be more, and it will be not be profitable. So what people are doing is that, you saying, see, the yield of memory chips will be near about 0%, since every chip will almost have a defect. So here we have to take a different philosophy. So what is the philosophy is that, now we found out that, as we discussed right now, that all the memory chips have more or less 100% of the chips will have 1 or 2 defects. So what is the idea is that you cannot throw them out. So what is the idea? You have to repair them and you have to ship it them. So what the people do is that they take the memory ICs, and while fabricating say 1 GB of memory, they will fabricate something extra. It will not be exactly 1 GB, it will be something more than that. Now what you do is that first you have to detect the faults. In case of combinational sequential circuit, we detect the faults, find that it is faulty, we throw the chip from the bin and you ship only the good chips. But here it will be a different philosophy. So what we do, as you know that almost all the chips have faults, so we fabricate somewhat extra part in the memory. 1 GB want to say you fabricate 1.2 or something like that. Now what happens? You find out that there is a fault in a chip. Now you also diagnose the fault. So So, in all memory we find some cells, there are actually redundancy and some extra cells are there in the memory, because you have to repair and sell. So, if you are saying that I am shipping a 1 GB memory, you cannot say save you are giving 512 MB kind of a thing, that is not possible. So, you have to somehow fabricate more area than what you are claiming, and then you have to discard, you have to repair the chips, that somehow you have to repair, repairing is not possible, somehow you have to do something with the fault part of your IC, and then you have to replace them with the redundant cells, and so that totally 1 GB you are shipping. It is something like, say you have to ship some 10 mangoes and 1 or 2 mango may be rotten. So, what you do is that you get some 12 or 13 mangoes, and then you find out that these 1 or 2 or 3 mangoes are not proper. So, you may demarcate them, because you cannot once the chips are fabricated, you cannot cut out a part and throw it off. You just demarcate the mangoes, and these are they are not the good mangoes, and still 10 or 11 mangoes are good, and you can ship them to the customer. Same philosophy is used over here. So, these are chip of 1 GB, you fabricate something more, you detect the fault as well as diagnose it. So, in case of combinational sequential circuit testing, you did not diagnose the fault, but here also you have to diagnose which area or which cells of your circuit are having fault. So, once you find out there is a fault, so you have to mark those cells, and you have to do some, there is always some multiplexing arrangement is there. So, this is from memory repair, we are not going to details, but the idea you have to understand is there is some kind of repairing is available, that is how do you repair it, you cannot repair. So, there are some 10 cells which are damaged, so there is multiplexing arrangement, in which case you can connect the inputs of which are going into the damaged cells to the extra redundant good cells you have been there. So, you connect them, and similarly the output of the failure cells should be again decoupled off, this cut off by using a multiplexing arrangement, and so that the output of the good cells which are extra redundant in market, redundant in your chips, can be brought into the normal memory area. So, by using some multiplexing, so once a fault is diagnosed, the corresponding cells is disconnected and new fault free C is connected in appropriate position. So, how you do? Sometimes we do it by multiplexing arrangement, and sometimes we achieve it by blowing up some laser fuses. That is, there is some you can have some multiplexing arrangement. So, you find out that this circuit is not working properly. So, how you demarcate it, as well as the connection input to the and output to the cells can be blown off by using this laser cutters or something kind of. Sometimes you can have a demultiplexing or multiplexing chips, and you can permanently select or deselect the, say for example, this is the input, which is input to the faulty what you can call faulty memory cell. This is for the good cell. So, what you have to do, there should be a multiplexer kind of a thing. These are marks. So, this is your input. So, it is this corresponds to 0. So, this corresponds to 0, this corresponds to 1. So, you should always find out that the input should never go here, because now it is faulty, the input should always go here. So, you know that if I have put a 0 in the multiplex, if you put a 0 in the marks, select line of the marks, so data will go to the normal part, and which is normal yet as of now, and if you put a 1 in the select line of the multiplexer, data will come to the faulty part. So, you permanently make this multiplexing input as 0, so that the fault data will always come to the normal extra memory cell. So, this can be done by using this permanently fixing the multiplexing select lines, so that your data is going to the normal part of this redundant cells which you have fabricated. So, it will go there, and the other part will not be used. Or sometimes you can also use laser technology to cut out, like for example, this is the this pin is coming to here, and both it is coming here and here. So, you demarcate that this is faulty. So, you blow that part using a laser, so that your data will come to the normal circuit. Similarly, you can do it for the output. But these are actually I am telling you in a very crude manner, because there are memory technologies involved, like memory fail detection, diagnosis and repair and all those things. So, that is out of scope of the present course, but I am just giving a very brief or a broad layman kind of an idea. So, if you are interested, you can read through any memory design book. Some of the references also you can find out in the course. Okay. So, now that is the two philosophical difference. So, first philosophical difference is that you have to diagnose the fault as well as detect and diagnose, which is not in the case of sequential and combination circuits. Secondly, you have to also repair. There is some redundant part of your circuit, so you have to also repair this. Okay, and second thing is that these are one philosophical stuff. Another philosophical stuff is the sole functionality of a cell is to store information and charge and discharge. That is, you have to store something and retrieve it back. So, use of logic gate. So the idea is that, so and logic gates are used in for many kind of other logical information. So, this whole structure of a memory is bit different from the structure of logic gates. So, these two will actually lead to the above 2 points will differentiate testing of logic gates from memory testing. So, this will actually lead to a different kind of fault model, and also this type of things says that you have to go for a repair and you should have some redundant parts, so that repairing is possible. So, because of this repairing facility is required, because almost all the chips have some some faults. So you have to repair it, otherwise your yield will be less than 1% or even less than that, and your memory architecture is very symmetric, and so many things can be stacked up in one place, and the functionality is nothing but storing a 0 or a 1 and retrieving that back. So these 2 points will make the philosophy of what you call the circuit testing different from memory testing. So in this course, in this lectures, 2 lectures, we will see what are the different memory fault models and how we can detect them. So that is the very basic idea we are going to see. So this is a memory architecture, sorry, this is actually memory architecture. This is the basic memory architecture or memory model. This is the basic memory architecture. So what you have, so it is standard memory, any book you can find out. So a memory will have cells. So this is a row decoder. So you give a address. So address will tell you that, say you give the address as 00010. So it will be the second memory location will be accessed. And you have to find out the column decoder. So this is memory will also be having some columns. So which part of your data will you access? Generally it can be if you want to access the whole word, so this is the whole word, or you can also access a part of it. So the column, it will tell which part of the column you have to decode, and there are sense amplifiers which are analog circuits which will take this data out from the required part. So okay, similarly, but if you want to write the memory location, then also you have to tell the address bus which is the which memory location, say for example 3. So this is the memory location which I want to write, and then the column decoder will tell which part you have to write. So this part will be selected, and there is some driver in the circuit which will tell what values you have to write. So this is a very basic memory architecture. So the components are, this is the memory cells, which is the stacked part, which is quite different from what you call our normal sequential and combinational circuits. And as I already told you, there is some redundancy over here. So if your some part of the cells get damaged, so what happens is that it will actually reorient the connection by blowing fuses and all whatever we discussed, so that this is a bypass. So what I am saying is, my mean bypass means, say that this part of the memory cell has gone bad. So this input will be coming over here. This is the sorry. So this is there is some. So this part of this was having some kind of a problem. So this was some redundant cell. So this is the redundant. So this will not join here. It will come back here, and from here it will come back. So this is bypassed, and this new extra redundant cell comes into picture. So this is how it is repairing that after you detect some faults. So this is a very broad outline of how a memory architecture works, or the memory architecture is. So as I already told you, whenever you have to read data from the memory, so the row and column has to be selected accordingly. This is the data bus based on the address and the row and column decoder, which is the appropriate part of the memory you have to select, that is get selected and get connected to the sense amplifier which sends out the data. So when you want to write it, so you have to do it same thing, you select the row and column, and then the driver will write back the values to this one. So what do you require to test RAM memory? You do not no other logical function excepting it just actually read some data, write some data, that is it. So what do you do? So you do not take for any kind of ANDing, ORing, all those things are not required. So what is the 3 tests you want to do? So required a value of 0, 1 to be written in a cell, that you should verify that each cell should be able to be written to be 0 and 1. So secondly, the value should be also be able to read from a cell. So if you write a 0, you should be able to read a 0. If you have to write a 1, you should be able to write a 1, and this should be possible in all the memory cells. Secondly, proper access is there. That is, if you want to access this part of the memory, so by giving the proper values in the row and column decoder. So these are decoder are basically combinational circuit decoder. They are basically normal circuits, normal logical circuits. So they are just decoders. So only this part is quite different from the what you call general combinational and sequential circuits. So the third fault point is that you should be, if you are wanting to address access this part of the memory, so you should be able to do it by giving proper values in the row and column decoder. So you should be able to select this, that is the actually fault to be tested for the row and column decoder. So you should be able to see that if I want to write a 0, I should be able to get a 0. If I want a 1, so I should be able to get a 1 from each memory cell, and as well as if I want to access the proper memory cell to the address, so I should be able to access the proper part. If I want to access this, and by this from virtue of some failure in the row and column decoder, I am accessing this part of the memory, so that is another type of a fault. So we should be able to check. So only these 3 types of faults we should be able to test in a memory block. So that's it. So based on this, we should be developing the fault model for the memory. So there, as I told you, there are three different types of circuits in the memory. So this one is the different part from this, which is main part to be tested, because which we are actually this is the compressed what you call capacitive kind of memory cells or whatever, that is different from the combinational sequential circuits. These are your standard digital decoders, so no general circuit, and the sense amplifiers and drivers, they are analog circuits, they are not digital circuits. So these 3 different types of circuits are there, and we should be able to test them. So now what is the idea? So idea, you see that we do not generally go explicitly for testing out these combinational circuits and these digital circuits. Rather than what we will do is that we will traverse each memory cell one by one, and we will try to write 0, get 0, we will write 1, get a 1, again we can also do the reverse, write a 1, get a 1, write a 0, get a 0. So, if we try to do it for all individual cells one by one in a sequential manner, so all the points will be tested, because you are going in a sequential manner, means first this, then this, then this, then this. That is, the idea is that row and column decoder should be working in a proper fashion, because otherwise I mean you may get jumbled up data. I mean you want to access this, you are accessing this point, so you may get a wrong data. So, if you are using this all this point in a very sequential manner, so the row and column in another sense get tested or verified. Similarly, sense amplifiers means you write some data, you are accessing some data. So, if you are writing some proper data, getting some proper data, that means sense amplifier is correct if you are reading the proper data, and if you are able to write it properly, then you are testing the driver. So, explicitly you need not test all these parts. So, if you sequentially write all parts of the memory cell, or in some predefined fashion, you know that I am writing this location, I am going to get back this location. So, some predefined order which you know, you write out the memory and you read them back, then indirectly everything is tested. So, that is what is actually we are going to do. So, what are the different fault models? So, the sense amplifier, as I told you, are analog circuits, and decoders are general digital circuit, but we do not consider digital at the gate level, and sense amplifier and analog circuits. We do not consider and test them, because analog testing is totally different. We are not going to test them in an explicit manner. Even the decoders, we are not going to state using a stack fault model or what you can call the bridging fault model. No, we are actually, I told you, we will write each sequence memory blocks or memory cells in some manner and try to retrieve them back, and then we just want to see whether everything is proper or not. And if that is the case, then we know that all the blocks are indirectly tested. So, what are the different fault models which are sufficient for memory block? People have found out stack fault, that is each of the none of the memory cell is stuck to 0 or stuck at 1. So, it can be, you can write a 0 and a 1. Second, the transition fault. Transition fault means you should have, if 1 is 0 is you have written, if you try change it from 0 to 1, so that transition up transition should be possible. Coupling fault, one very important. So, these are two standard fault, like you should be able to go from 0 to 1 and 1 to 0. So, these are other very important, these are all also available in sequential and combinational circuits, although we have discussed only about stacked models, but transition fault, delay faults, bridging faults are also considered in case of a sequential and combinational circuit. But these are some of the other very important tests which generally exist in memory, which is called the coupling fault. This is because the memory cells are like this, and they are very much stacked with near each other. So, if you stack very much these cells of a memory near each other, so what may happen is these two cells may get coupled. So, any changes here may affect here. Similarly, if you see like this, so if you have a 3 memory cells, so see this is the memory cell, so it is surrounded by some other cells and they are very near each other. So, whatever is happening in the periphery of this may affect this cell. So, these things are called coupling fault, neighborhood pattern sensitive faults, and address decoder and etc. faults. So, we will see that it can be automatically covered if you are covering this. So, that we will see. Okay, so, this coupling fault and neighbor pattern sensitive faults are all happening because the memory is very much stacked and all the cells are very near to each other in a very small area. So, anything happening in the periphery may try to affect the central part or the one cell or the other. So, this coupling fault and neighborhood pattern sensitive faults are mainly new kind of faults which you test in memory. The reason behind this is very interesting, because everything is stacked up in so near to each other. So, none of the cell can remain very much free, or it can move free under the fault case from compared to its neighbors. So, that is why this neighborhood pattern sensitive faults or coupling faults are have taken a very important role in memory. So, we will slowly see, elaborate one by one each of them, and then also see test techniques for them, and we will see why they are more relevant in a memory. Okay. So, first is the stacked fault. So, how is the stacked fault in a normal case? So, state S0 represents that some memory state is having a 0, and 1 means that memory cell has been written a 1. So, if you write a 0, initially if it is 0, that memory cell, so if you write a 0, W0, so you come back to this one. So, if you want to write a 1, so you write W equal to 1, you go to state S1. Similarly, if the state value is 1, if you write a 1, so you will be in state S1. And if you write a 0 from this one, you go to state S0. This is the normal state diagram for a good cell. But now, if you see if you are stuck at 0, so what is going to happen? So, you will be only in this state, that is S0, and if you write a 0, so no problem, but if you try to write a 1 in the cell, you will be in that same state. So, that is actually for stuck at 0 fault. Similarly, for stuck at 1 fault, what is going to happen? You will be only in this state. So, if you write a 0, you cannot go back to the state, okay, you will be only in that one state only, and if you write a 1, that is okay. This is the case. So, this is the state diagram for a normal memory cell, and the state diagram for stuck at 0 and stuck at 1 fault. So, that is what is being elaborated here. So, what happens? So, stuck at is in logic value, is always 0 or 1, just like the stacked fault in a sequential or combination circuit. In this case also, stacked fault in a memory is 1, in which the logic value of a cell is permanent 0 and 1. So, in state 0 it is 0 and state 1 is 1, but if you cannot move from this to this, so just stacked 1 or a stacked 0 fault. Now, transition, next is the transition fault. So, transition fault is what? Transition fault means a transition in a cell, if a transition fault in a cell fails to make a 0 to 1 or a 1 to 0 transition. That is, if you want to move this way, that is 0 to 1, if you want to move in a cell, so it will be stuck to 0, it is not allowed to do this. This is called a rising transitive fault, or you can call up transitive fault, something like that. And also it may be happening that you want to go from a cell from 1 to 0, but that is not possible because the fault still remains as a 1. So, you can call it a down transition fault. Okay. So, these up and down transition faults are also very much prominent in case of memory cells, but it also exists in a combinational circuit, even and sequential circuits, even if you have not discussed that. But I mean, in case that is actually called delay to rise and delay to faults are there. So, that you want to go from 0 to 1 within some fraction of a, I mean in some nanoseconds, but it does not happen, it waits for a long time because of the delay faults. So, these things can also be mapped to transition faults in a sequential and combinational circuit. But anyway, we are now looking at it from the memory perspective. So, just look at this state diagram for a up transition fault. So, this is not allowed. So, you see, but this is not a stacked 0 fault. So, there is a difference between this one and a stacked 0 fault. So, in this case you see it is a 0. So, if you want to write a 0, so obviously it will be there. If you want to write a, if you want to write a 1 over here W1, so from 0 to 1 you want to go, that you cannot go. So, you will remain here. Okay, but this is not a stacked fault. So, there will be a state of 1. So, if somehow some is not 0, somehow you have written a 1 in some case and then the fault has occurred. So, from 1 to 0 you can come back, from memory from S1, that is 1 in this cell, you can come back to this one, but after that you cannot rise the value, and if you want to write a 1, so you will be in that self loop. But if it has been a stacked 0 fault, so this part would not have been there, as we have seen. So, there is a big difference between a stacked 0 fault and a transition fault. So, transition fault means you cannot go from 0 to 1, but if before the occurrence of the fault, it could have been that it is the case that 1 was somehow written in this cell, because when you start up a memory, the cells are all filled up with garbage values. So, it may be possible that that particular cell had a value of 1. So, you can come from 1 to 0, but once you want to go for high, so you cannot do that. Sorry, this is a 1, so it will be remaining there. So, this is a up transition fault. Similarly, you can also have a down transition fault in this way. Now, very important is the coupling faults, because as I already told that memory cells are very near to each other. So, I mean if two people are very near each other, then the behavior of one person will obviously affect the other, and if one person is very near to about 10 other people, so you can already know that the character of the person who is around 10 other people will have been influenced by the other 10 other people near him or her. So, now in the same case, as memory is very much stacked, so I mean say it is a cell, so you have something over here, so all of the people around here, so the effect of all of these cells will be affecting this central cell, I mean that is this one. So, that is why coupling fault means there are two cells, so one is being coupled with each other and they are affecting each other. So, that kind of fault is called a coupling fault. So, it says that coupling fault, as the name suggests, implies deviation from normal behavior of a cell because of coupling with other cells, because of getting I mean what you call getting influenced by other cells. So, it happens. So, I mean you know that a cell can be, say this is a fault cell can be coupled with n, say let there be n cells in the memory. So, n plus 1 cells in the memory, let us assume. Then for this particular fault case or the faulty cell, so it may get coupled with one cell. So, 1 means it is NC1, any one of them. Then it cannot get coupled with 2 cells. So, it will be how much? NC2 ... you can be n my n Cn. So, it can get coupled with any one of the n faults, it can get coupled with 2 cells ... it can go to coupling with all n other cells. So, the number of coupling faults can be extremely high, it is NC1 plus NC2 ... NCn. So, this is a very high in number. So, that number of different all possible fault cases will be extremely exponential in number. So, you cannot go for that. So, standard it is taking that, it is called the 2 coupling fault model. So, it assumes that one fault can be one cell can be coupled with at most any other cell, and you can try out with all other cells, right. So, if there are n cells, so you can get coupled with any one of them. So, there will be n different types of faults only compared to NC1 plus NC2 ... NCn. And just like stacked fault model, we will have found out that it gives reasonably good coverage as well as good confidence on your fault testing. So, this is called 2 coupling, because any 2 cells can get coupled than this one. So, if there are n cells in the memory, so there can be Cn 2 number of coupling faults. obviously, and to reduce that, so you generally you can you can understand that. So there is a big memory like here, so this cell cannot be coupled with this cell because they are so far from each other. So you can make up a window that all this stuff, or you can make a shifting window kind of a thing. So this window will shift here, then this window will shift here, and this window will shift here. A shifting window concept, okay, like this one. So this is one window. So then it will be again shifted. This window will be again shifted here, this window, we all know the shifting window concept. So that means we can consider that two cells which lie within a certain square area, like for example in this case only cells within this area can get coupled. That means the cell here cannot have a coupling effect with this one because distance is higher, but this cell will have a coupling effect with this one. So it is a moving window kind of a thing. So you can move the window here, you can also move this window in this direction, or move the window in that direction. So by this one you can reduce the number of all possible coupling from NC2 to this one. So there are different type of this. So the number is fixed. So it is at max NC2 if you are considering 2 gate coupling faults, and secondly also we can reduce it further down from NC2 by looking at the study of the proximity, that these two cells are very near each other. So by moving window concept you can do that. So now here we will be studying 2 types of coupling faults. There is called inverse coupling faults and idempotent coupling faults. So there are 2 different types we will see, and that will make the things more clear. Okay, so first we will see the inverse coupling fault. So here actually you should see that there is a cell called I and there is a cell called J. So these two things are getting coupled with each other and having the problem. Okay, so this cell actually, this is called the coupling cell and this is the coupled cell. Now you see the coupled cell actually is the faulty cell. So this guy affects this one, this is normal. So this coupling cell affects the coupled cell and this guy is getting the fault. So that is the basic idea. So in a inversion coupling fault we write it I and J, then 2 cells I and J, there are transition from 0 to 1 or a transition from 0 to A in cell J, that you go from here or you go from here, that is the cell J will develop an unwanted J something in cell I. That is actually the inverse coupling fault. So in inverse coupling fault what is happening? So there is a cell called N and there is a cell called I. So this is the coupling cell and this is the coupled cell. So if this 0 to 1 or 1 to 0 some changing is happening in the cell J, then it is affecting the coupled cell in some undesired way. So this is the faulty cell and this is the fault causing cell. So what are the types of inverse coupling thing? So one is a rising and flip. That means a change from 0 to 1 in cell J, that is a 0 to 1 in cell J complements the content of cell I. So this gets complemented. So if it was 0 now it will be 1, and if it is 1 it will be 0. So any 0 to 1 rising here will complement this cell, complement the content here. Similarly, down it can also be falling, 1 to 0 here will again call this undesired change. So this is called the falling and this is called the rising inverse coupling fault. Okay, so now again let us try to, you can represent with this one with this diagram. So this is normal. Now for that we know that we require I and J. We require 2 what you called for representing coupling fault. So representing stacked faults we just required one state S1 or S0, but in case of coupling faults you know that we require 2 cells to be used. So the idea here is that, so I have 2 cells, so I and J. So there is S0, S01, 10 and 11, basically equal S, I and J. So first bit corresponds to state I, second bit corresponding to state J. So if you see that, so 00, 01, 10 and 11. So if I am in state 00, so if you write 0 at I, if you write 0 at J, so there will be a self loop. So if you want to write 1 at J, so we will go to state 01. From here if you want to again write back 0 at J, so you will come here, right. So from here if you want to write 1 in the cell I, so it will have to, this is the case, so it will be 1 0. This stands for I and this stands for J. So from here if you want to write 1 at the cell J, you write as the 1 at J, you go here. Similarly the whole stuff can be explained. Now we will see the inversion coupling fault. So some example we will see. So we are going to see this one is the inverse coupling fault. So this is state diagram for an inverse coupling fault. So you see these are the 2 thick rows I have marked, they correspond to some kind of a inverse coupling fault. Now you see what happens. So in this case this transition, all other transitions are normal, these are the 2 transitions correspond to the coupling fault. So let us see what is there. So in this case you are saying that write a 1 in J. Okay, so what happens? S00, you are going to write a 1 in J. So you should have S01 because you are writing J equals 0 to 1, this is the transition. But because of this inverse coupling fault, this is a up coupling fault. Okay, what happens? This value gets complemented. So unnecessarily this will become a 1 and you will go over here. So if you have in the normal case, we should have the transition from here to here because we are writing a 1 in J. Okay, but because you are this up, so also a value of x, a value of I is also changing from 0 to 1. So therefore we are not going to S01, but we are going to S11. Similarly, also then another fault over here, like for example the down coupling fault. So in state J, you write it was 0 and you want to write a 1 over here. So you are going to make a that initially it was a 0 to 1, initially it was the rising coupling fault, and now this is the this was the fall. Okay, so okay, they are both the same. Actually, you can have it in both the ways. So this is actually we are both showing the rising coupling fault only. The down coupling fault, I mean the fall coupling fault can also be shown in a similar way. So in this case, you are writing same thing as I told you. You write a 0 to a 1 in the cell J, and unnecessarily this S also gets complemented. Similarly, here you are writing a 0 from cell J to 1 in cell J. So it's a 0 to 1, and the content of this guy is the content of cell I is also getting changed from 1 to 0. So it should have been, we should have gone here. If you want to write a 1 in a J, from 0 to 1 in a J, you should have gone here, because the content of I you are not touching by this one, but that is by this one this W1 at J, but because of this coupling fault, the content of cell J is changing, is also getting complemented from this one. So you have this 2 extra transitions for this up transition fault. Well, similarly, you can easily draw for down coupling fault also you can draw, that is, I mean if you want to change the cell value from what do you call this value of from 1 to 0, like for example if you are having a cell from here, you want to this one you want to change it from 1 to 0, that value. So it is a falling. So now this value of x1 will get complemented. So you will, instead of this transition, you will have a transition from here to here. So you are changing this 1 to 0, that is you are going for a down in J, but along with it the value of x, that is 1, will also get complemented. So this transition will not be there, you will have a transition from here. So this way you can design a model for a down, I mean this fault, that is actually called a this falling inversion coupling fault. Okay. So this way you can draw the state diagrams. For all this was about up, so you can also draw it for the down. Okay, now the other type of idempotent coupling fault that we are going to see. Okay, so what are the different types? I mean, let us. So in this case, this was a what you say is that. So inversion coupling fault, actually there is a complement from 0 to 1 or a 1 to 0. So that was about the inversion coupling fault. Other type is an idempotent coupling faults. Okay, so idempotent coupling faults are a bit different. So what is the idea? So in this case again there are two cells I and cell J. So this will actually this is the coupling cell, this is the coupled cell, this is normal, and this actually causes a fault effect. So what is that? There are 4 types. Rising. So if there is a rising from here to here, then in this case the value of x will be set to 0. Whatever may be the cell, what is change in 0 to 1 at cell J changes the content of I to be 0. If it is 0 to be 0, fine. If it was 1, it will be 0. It is something like up here will actually make this stuck at 0. Similarly, it can happen that rising 1. So if it is a rising at n, so it can make this stuck at 0. Similarly, the other way, if there is a fall in this the fall in J will set the content of I to be 0, stuck at 0 at I. Similarly, if there is a fall in cell J, the content of I is to be 1, that is kind of stuck at 1 fall. So in the other case, we had a transition. So if the rise here, so that was about the inversion coupling fault. So if there is a rise here, so there is a flip. If there is a rise here, there is a flip. Okay, so and in case of idempotent, it is slightly different. So even if there is a rise or a fall, so the x I actually the coupled cell will either be stuck at 0 or stuck at 1 by default. So, there is slightly difference in this. So, you see this is the idempotent coupling fault example. So, in this case what you have done? So, in this case you are changing from you are changing from 0 to 1. So, this is the case, and now it is actually making the stuck at fault. So, in this path you are changing J from 0 to 1 and value of x gets changed to 1. So, it is stuck at 1 kind of a thing. But now, if you remember the previous incidence, that is the reverse coupling, the inversion coupling fault. So, there was another path over here. So, in this same thing was happening, we are changing the value of J from 0 to 1. So, the value of x was getting flipped, I was getting flipped from 1 to 0, but in this case it is not a flip. In this case the value of I is actually permanently stuck at 0. So, whenever there is a change in I from 0 to 1. So, you do not have this transition in case of a idempotent coupling fault compared to the other case of a inversion coupling fault. Now, third fault model is the bridging fault. This is also very well known fault model in case of what you can call our circuits also, in combinational sequential circuits also we have bridging faults. So, what is the bridging fault? It is similar stuff like what you can call this coupling fault and all. So, in this case what happens? There are two cells, say I and J. So, both the cell will affect here each other. So, that is very important. In the case of coupling fault, there was one person who was dominating and the other person who was getting dominated. So, this J was affecting I kind of a thing, but here both of them will affect each other because they are getting bridged. So, this is a bridging fault. So, there is something called AND bridging and something called OR bridging. In case of AND bridging, what is going to happen? So, if there is a value of 0 here, 1 here, so both of them will be ANDed, the answer is 0. So, we will get 0 0 over in both these cells. This is called AND bridging fault. Now, if both these cells like cells I and J is here. So, as I said 0 1, so it is the AND bridging fault. So, this guy will be getting changed to 0. So, in this case I is affecting J, but because it is the AND bridging fault. Okay. Now, is the OR bridging fault, let us say that in case of OR bridging fault 0 or 1 or is the 1. So, in this case this 1 will be converted to 1. So, cell value will be 1. So, in case of OR bridging fault the value of J is dominating over I kind of a thing. So, both can dominate each other. So, there is nothing called one is the dominator and another getting dominated. So, both of them can both of them can get affected by the other, and in case of, so if the value is 0 0, the output is 0 0 in case of a AND bridging, because AND of 0 and 0 is 0, 0 1. So, both of them will be 0 kind of a stuff because of what you can say. AND of 1 and 0 is 0, 1 0 both will be 0, 1 1, then both of these will be, because the 1 and a 1 is this one. So, in this case this one and this one, in case of the AND bridging fault, they are not getting affected by the AND bridging fault, but here this what you can call these two cases are affected by a AND bridging fault, like because 0 is one cell, 1 is in another cell. So, both will be converted to 0 0. So, there is a problem. Similarly, in case of 1 0, but 1 1 the output, even in under case of AND bridging fault also 1 1 means the output will be 1 1 kind of a stuff, and 0 0 the output will be a 0 0 also. So, no problem, there is no change in case of a fault in case of a AND bridging fault. So, if you are taking a OR bridging fault, so this is okay, 0 and 0 or 0 is 0. So, this will be 0 0, 0 and a 1, it will be 1 and 1 in case of OR, 1 0, so it will be 1 and a 1. So, this is the problem, and 1 and a 1 is OR is 1. So, you get a 1 1. So, in case of OR bridging fault, so this is what you will be getting. So, this part will be no problem in 0 if a cell has both the cells as 0 0. So, AND bridging, OR bridging, there is no problem, but all these three are having problems in case of OR bridging, and if you are using a AND bridging, so only this is not going to have a problem in case of AND bridging. Only these two are going to have a problem in case of AND bridging. So, this is about the AND bridging fault. So, as I told you, these are the OR bridging faults, like 0 0 to 0 0, 0 1 will be 1 1, this will be. So, these are the two gates which are having some kind of a problem in case of a OR bridging fault, correct. So, and in case, that is what I am saying, yeah. So, in case of AND bridging or OR bridging, whatever you take, so you are going to have a problem mainly with these two blocks. These are the two things, because in both AND and OR whatever you take, these two things are absolutely proper. So, in case of a OR bridging fault, so if I and J both of them can affect each other, there is nothing called dominating or being dominated, but they should have different values to be having problem in case of fault. Like if both of them 0 0, there is no problem in case of both AND and OR, because 0 or 0 is 0 and 0 and 0 is a 0. If both of them 1 1, so ORing them will get also 1 1, if both, and ending of these two will be again 1 1, so no problem. But if it is 0 and a, but if it is 0 and if it is a 1, then in case of OR bridging fault, this guy will be dominating this one in case of OR bridging fault, and if it is AND bridging fault, then this guy will be dominating this one. So, this is the case. So, those cells should have different values to be getting affected by a bridging fault. Next is something called, which is very important in case of what you can call this memory testing, as I was again emphasizing, is called the neighborhood pattern sensitive faults. That is very important. That is, in case of memory, you have this type of cells kind of a thing. So, this is a cell. So, around that you will have another large number of cells. So, all these will try to affect you. So, it is being affected by neighbors. So, this type of fault problems you can see is not available or is not there, or not actually studied or required in case of sequential and combinational circuit, because there there is nothing, no symmetry is there. Neighbors will affect, but this effect is less, much less compared to a memory cell, because in memory everything is very much compact, placed very near each other, and that is actually creating the problem over here. So that is why we say that different kind of memory faults in this one. This is actually called memory. One of the most and different kind of fault model in memory compared to logic gate circuit is the neighbor is this one. That is what I told you. So one cell may be very near to each other, so you should be here. For example, I mean different examples are here. We'll come into that. So basically the idea that this is the case. It is surrounded by things which are very near and compressed in nature, so they are affecting it. So that is why it is most important fault in case of memory and quite different from circuit, I mean other logic circuits. So there are two type of neighborhoods that are being considered. So you will see one, these are type 1 neighborhood. So we mark this cell as 0, 1, 2, 3 and 4. So these guys are affecting this cell. So this is one thing. So it is assumed that the diagonal elements are bit farther away from this cell, so they are not having that kind of effect. Because you see, if you can generalize the neighboring concept, you can say that this is one neighborhood, you can say that this is another neighborhood, farther area will be another kind of a neighborhood. So your neighborhood shape can also be in this way. So there are different paradigms or what you can call different type of, like for example like coupling. So you say that 2 cells can couple, 3 cells can couple, 4 cells can couple and so forth. But in case of the neighborhood, to define a neighborhood is a very exponential problem, in fact infeasible kind of a problem. Neighborhood can be anything. You can also consider it as this guy, this guy, this guy and this guy as neighborhood, which are diagonal to each other for a very specific case type of circuits. Also you can say that these things, all these things can be considered as a neighbor. So and also you can say that these things are all considered as a neighbor. This one, this one, this one and this one are considered as neighbor. Here we are not considering the diagonal elements are not considered. So the idea is that neighborhood can be considered in any type of fashion, and that is actually going to kill you. So you cannot have any type of neighborhood defined, and it is not actually required because of the exponential nature in the problem. So what you do is that, so we define in testing, and people have done statistically and many other methods, they have found out that there are two type of neighborhoods which are, which is enough to do your testing on, which can be reasonably lower in complexity as well as it can reasonably give you a good coverage and confidence. So this is one type of type 1 neighborhood in which you have this cell. So these things are not, the diagonal cells are not involved in this, and 0, 1, 2 is this cell which is under effect, 3 and 4 are the neighbor cells. Okay. There is another type of neighborhood, so it is a bit more complex. So it is, they also consider the diagonal elements can also be like this one also to be involved in this coupling because they are all nearby. Also so there is a bit more complex, but takes more number of cells into consideration, making the fault model more effective. So here it will be 0, this is 1, 2, 3, this one is 4 is the affected one, 5, 6, 7, 8. So this is a more complex coupling fault, neighborhood fault model, but you can also consider the third area, fourth area, making it horribly complex and people do not consider it. So in testing we consider only these two type of this one. So type 1 is okay, but for type 2, it's a bit more complex stuff which we will not discuss, because you think that you have to also consider 8, 1, 2, 3, 4, 5, 6, 7, 8 different type of, 8 different neighborhood cells you have to consider, while in case of 1 you need to consider 0, 1, 2, 3, only 1, 2, 3, 4, only 4 cells which is in the periphery. Okay. So now we will see different type of 2 or 3 different type of fault models in this one, in the case of neighborhood pattern sensitive coupling faults. So one is the active one. So what is an active one? So active one says that, so V0, V1, V3, V4, these are the 4 cells which are actually periphery of this one, 0, 1, 3, 4, and this 2 cell is actually being affected. So that is why we write 0, 1, 3, 4, they are all these cells which are very nearby this one. That is, you can say that 0, 1, 3 and 4, and this is your affected part, this one, right, and V cut is the value of some cut, something like that. Okay. So now this is one type of a fault. So what is this? Active neighborhood pattern sensitive fault. Active means there should be some activity in these 4 cells where this one. So it is saying that initially the value of Fe is equal to 1. Fault value is equal to 1, this value is equal to 1 initially. Now you say that all the other values were 0, 0, 0, 0. These are the 4 values. This guy, this guy, this guy, this guy, where values are having a, sorry, this value was having a 1. Initially it was 0, 1, 1, 0. Initially this configuration was nothing but initially it was something like this. It was having the value of 0, was having the value of 0, 1 was having the value of 1, this one having the value of 0, this one was having the value of 0. Fe was having the value of 1. Now it says that, what is the fault? There is a slide, there is a drop in this one. So this one changes to 0. So if you do this, it says that this cell also gets affected and it gets converted to 0. Now why is it that kind of thing? So in these things, so near about everything 1, now it is 0. So all of them together pulls it down to 0. But initially it was not 0 because this cell was also a 1 and that was actually helping it to be a 1. So now if you make this guy to be a 0 for some reason, so this by being periphery of all other zeros get changed to 0. So, it is having a 0. So, because of this activity from 1 to 0 in this one, this gets 0. So, this is one example of an active neighborhood sensitive fault. So, that is because of some activity here, here or here, they are also trying to pull this guy to 0 and 1. So, this is one example of this one. So, this is called active, because active means some changes in any one of this neighborhood, change some 0 to 1 or 1 to 0, they are actually happening a change over here. Okay? So, this is called active. There is something called passive. There is something called passive. Now, what is called a passive? We call this as a passive because in this case, we will not have any changes in the neighborhood cells. Because of some passive nature only, by 0 or 1, some nature, some pattern nature will also affect this internal part. We will see. So, in this case, we say that V0, V1, V3, V4. So, V1, V0, V1, V3, V4. So, these are some values. V cut is the value of the cell under test, that is 2, and these represent the value of the neighboring cells, and Fe represents the fault in the cell. So, there are 3 kinds. So, just see the example is better. It says that due to some pattern over here, okay, so these are your cells. So, this 0, 1, 2, 3, 4. Okay, this is Fe. So, he says that 1, 0, 1, 3, 4, because of some values over here, like you can say that some all values like 1, 1, 1 and a 1, something like this, you cannot change this value from 0 to 1. Or sorry, we can say this, all these things are 0, let us assume. So, let us assume all the values are 0 over here. So, now it says that V cut, this V cut means this middle cell, that is cell under test. So, you want to move it from 0 to 1, but all other peripheries are 0, all the other zeros, 1, this is point value 0, value 1, value 3, value 4, 0, 1, 3, 4 kind of, 0, 1, 3, 4, all these are 0. Now, because of this everything is 0 nearby, so it will not allow this center part, that is cell number 2 or Fe to rise from 0 to 1. So, it says that you want to rise the value of the cell under test from 0 to 1, initial value of cell under 0, but it is not allowing to do that. This is one kind of a fault. Okay. So, similarly, it says that this kind of one kind of fault can be like, say for example, if all these things are now 1, 1, 1, 1, this is also 1. Now, you want to say that you want to make this 1 from 1 to 0, that is you want to make it fall, but because all other peripheries are 1, you will not be able to do that. So, this is another kind of a neighborhood pattern sensitive fault which is passive in nature. All these are 0 or all these are 1s. So, passively they are trying to hold the value of the other neighboring cell which is being affected. And in case of active, what was the thing? Same thing was there, but there used to be some kind of activity in this cell or this cell or this cell which used to be changing the value. So, these are two slight difference. Another thing is that, I mean, because of some pattern sensitive fault, I mean because of this passive fault what you are doing, you are actually unnecessarily, the cell cannot be changed regardless of content. Like in this case, this cell is there. So, some values you put like 0, 0, 0, 0, or if you put 1, 1 or some value is there, but now this cell becomes fixed for some nature. You are trying to change the cell to 0 to 1 or 1 to 0, but you are not able to do this, cell becomes fixed at the value. So, there are 3 types of neighborhood pattern, passive pattern and network pattern sensitive faults. So, why they are called passive? Because in this case some values are there in cell number 0, 1, 3 and 4 and they are affecting the cell under test which is in the center. And why it is called active? Because here some patterns are here and there is some activity either here, here or here on multiple places, and that activity is changing some fault over there. That is why this one is called the active in nature and is called the passive in nature. And they are very important in case of memory testing, because memory architecture is something like that, the cells are very much coupled and near each other. So, what happens, one cell is affecting the other in a neighborhood fashion. This is like an example that if a good person is in among us the friendship of several bad friends, the person will try to become bad, and in the other way similarly, like if a bad person is among all other persons which you are good, I mean if a person who is bad and but he stays with good people, then it tends to happen that he also becomes a good person. So, there is a neighborhood is having a very much effect on the cells. So, that is one another fault model we have seen. So, there is last part is actually address decoder faults, which we call address decoders are nothing but they are another type of a combinational circuit decoder, and we do not test them in a normal manner like a combinational circuit, because our idea is that if we do not want, because it is coupled to a memory. So, its job is only to access some memory locations and deliver the value by the what you can call sense amplifier and the driver cells. So, there are actually two other as part of the circuit, as I told you, where the analog parts, which is the sense amplifier, which sends the values from the circuit, or something which drives the value to write a memory cell. So those parts also will not test explicitly, and similarly the decoders also will not test explicitly. So what we will do is that, because the idea of the memory decoder is that you select some cell, you write it and you retrieve it back. So this decoder should be able to select the cell properly. That is what is the idea. No cell is accessed for a certain access. I mean, so from the context of memory testing, 4 types of faults you can consider in address decoding. With a particular address, multiple cells are simultaneously accessed. This should not be the possible. Should not be the case. A particular cell should be accessed with a multiple access. This should not also be possible. That is, say this is a cell. So this is a cell kind of a thing. So it should be able to be accessed with only one particular address, that is the proper address. So what is the idea? With a particular cell address should be a particular cell can be accessed with multiple address, that is should not be possible. That is, say it is cell number 5. So you should be able to access only with cell number address 5. It should not be with 3, 2, 1, 5. So with all 3, 2, 1, 5 you should be able to access this, should not be possible. Okay. Secondly, with a particular address multiple cells should not be simultaneously accessed. Just right. You want to say access 5, so this should be accessed. Simultaneously you are accessing this part, and for some other cell you are accessing this part together. That should not also be there. Okay, and it should not be there something like that, no address for a certain cell. Like for example, there is a cell, this cannot be accessed by any memory any memory address. Right? This cell is say 7. So by 7 you should be able to access this. It should not be the case that you are trying to put, you should not be able to access it ever. You give 7, you access some other cell, and you cannot access it ever. So that should not all be possible. So you say that no address access a particular cell. This should not be the case. No cell access for certain address. So these are some of the cases which are actually address decoder faults. But generally the idea is that we may not be able to go for testing of these things in this explicit manner. Rather than what we can do, we can access these cells sequentially. So if you are able to access all these cells sequentially, write proper values and read proper values, then you can be very much sure that none of these faults are there. Because you should be able, because the idea is that in one time you can access only one cell. Because if you are accessing multiple cells, then you are, whatever you are writing will get some other kind of output. What you are expecting, that output will not be there, because some cell here is being accessed, another cell is being accessed by a single address. So that will not be possible. So also these things will not be possible if everything is proper. With a single address, multiple cell cannot be accessed. Like with a particular access with multiple, that will also not be there, because you are asking for something, you are getting something. That means what? And if you are trying to do it for all cells, that means all cells are accessed, all cells are properly accessed by a unique address, and no address is accessing more than one cell. So if you just access all these cells one by one and check everything is proper, then all these things will be done in a proper way. Okay. So now, that was about the memory faults. Okay. So in the next lecture what we are going to see, because you see this is very simple, right. So the idea is that you have to access a memory location, you have to write 0, you have to read 0, and so forth. So that is the very idea. So here you did not propagate the fault value to the output, here you did not sensitize. All those things are not required. It is very simple, because the memory should be able to hold a 0 and a 1, and you should be able to retrieve it when required by a proper addressing mechanism. So that is what we are going to do. You are going to each cell one by one, write a 0, read a 0, write a 1, read a 1. This is the thing. If you do sequentially for all the cells, then your job is done. So here you do not require standard ATPG algorithms, D algorithms, propagating the value to the output, sensitivity is not required. Access each cell, write a 0, read a 0, write a 1, get a 1, and you are going to be done. Okay, so this is what is called the testing of memory faults. So in the next lecture we are going to see how we can go about this. This is a very famous testing for the March test, so which we will be seeing in the next lecture. Thank you.